Hello, Chem 2 students. Mr. Keister here with you again. This is the video for Tuesday, September 1st, which is our scheduled 9th day of school for the fall semester. My disclaimer, though, always keep in mind the dates could change for a variety of reasons, but the lessons will remain the same in the same order regardless of that. So let's look at today's do nows, our agenda for today. Today we're going to pick up and we're going to go over page 19, which is a review of density and the introduction of the term specific gravity. Yesterday, we did a review over mass and volume and the graph between mass and volume, which of course yields density. That was your homework for today. I am not collecting that, but please make sure that you check your answers. They are either posted on the backboard if you are here in person at school, or they will be posted on the answer keys page on my Canvas page. If you are at home, you can check your work there and make sure you do. Today in class, we will continue on in the notes regarding density and specific gravity. You are to complete the assignment, page 19, for tomorrow. I will be collecting that assignment for a grade, by the way. Also, tomorrow we will be doing a lab. Okay. We have a mastering assignment that is also assigned, Unit 11B over measurement. That is due tomorrow by 7:30 a.m. That is tomorrow morning at 7:30 a.m. Hopefully you've already been working on that. Please do not forget that due date and time. All right, so let me unfreeze the screen here and we can get to today's lesson. Okay, so we finished up yesterday looking at mass and volume and density and the relationship that how density comes about is based on the ratio of mass to volume. And a mass and volume graph then, when you plot mass versus volume of a particular substance, you end up with a straight line, positive slope. And the slope of that line, which again, remember, slope is the change in y over the change in x. In the case of a mass versus volume graph, the change in y is mass, the change in x is volume, and the ratio between those two then is density. And thus then the slope of the line on a mass versus volume graph is equivalent to the density of the substance. Okay, you need to remember that. And then the equation for density, D equals M over V, is thus derived directly from that graphical relationship. So let's then move on. We've said this already right here. So the most common unit for density are grams per ml for liquid, grams per centimeter cubed for solids. Remember that an ml and a centimeter cubed are equivalent. All right. If you took a cube that is 1 centimeter by 1 centimeter by 1 centimeter, or 1 centimeter cubed, it will hold exactly 1 ml of a liquid. So those two units are equivalent. And grams per liter for gases. So all of these units are good for density. They are used out of convenience more than anything. Normally in chemistry, we're measuring volume in mLs and substance in grams, so that makes sense. Normally with solids, if it's a regular solid, you can measure its volume directly, and so a centimeter cube with a ruler, and so a centimeter cubed is an appropriate unit there. For gases, an ml is quite a small volume of a gas, so a much more convenient one would be a liter, and so there again, that's why those are used. Actually, the standard SI unit for density is kilogram per meter cubed, but for the purposes of chemistry, a kilogram is a very large mass, and a meter cubed, which is this like this by this, is a extremely large volume that we would rarely use. So again, we use these other units out of convenience. But any unit, all right, any unit whereby you're using a mass unit of some kind over a volume unit of some kind would be appropriate for density. Okay. We just use these standard units because then we were able to compare them much more easily. So to solve for density, you have to have both of those measurements, mass and volume. So in a lab situation, you got to be able to measure both of those in order to find density. So let me advance the page here. So think about how you would measure those two things, given the type of substance, the state of matter of that substance that you're working with. So for solids, measuring mass is quite easy, I should say. You can do it directly with an electronic balance. Okay. For liquids, though, you can't pour a liquid on an electronic balance. It's going to make a big mess. So we're going to have to use a container. So that would be indirectly then, and we would need a container. So as we've said before, you could do one of two things. You could put the container on the balance and find its mass, pour the liquid in the container, find the combined mass of the two, and then subtract the two. Or with our electronic balances, you could put your container on there, hit the on or tear button, which will zero it out, pour your liquid in there, and all it's measuring is the mass of the liquid. So a little shortcut there. For gases, well, gases take the shape and volume of their container, so we certainly can't do it directly. You're going to need a container for a gas too, but in particular, you're going to need a sealed container. All right, one you'd have the ability to seal. So, one with an opening, put the gas in it, be able to close and seal that opening. To then find the mass. Now, gases don't weigh much, all right, but they do definitely have mass. Okay. And if you don't believe me, put a balloon, put an empty balloon on an electronic balance. Blow it up with your breath, tie it off, put it back on the balance. The mass increases. Right? Not by a lot, but it does increase. Right? Because gases, of course, are not very dense. How do you measure volume? All right. So for a regularly shaped solid, we said we could measure its dimensions. So that can be done directly. Measure its dimensions. Normally with the ruler. Measure dimensions and then use some geometry equation to determine its volume. For example, length times width times height if it's a rectangular solid. For irregularly shaped solids, though, such as this, kind of hard to find measure the dimensions of this thing. So how do we do it? Well, we do it, you probably remember this, we do it via water displacement. So that would be indirectly by water displacement. For liquids, that's the easy one. You can measure the volume of a liquid directly. That's what a graduated cylinder is for. And then with gases, of course, here again, gases take not only the shape, but also the volume of their container. And so you have to be able to, contain them. And so, again, indirectly, need a sealed container. Again. And thus, whatever the volume of that container would be, that would also be the volume of your gas. Okay? All right, so let's go on to the next page. Let me advance it. Go. Now, I want to introduce a term that perhaps you have heard in some other science classes, perhaps you have not. This is specific gravity, all right? So specific gravity it's basically a comparison of the density of a particular substance as compared to the density of a reference substance. All right. So for liquids and solids, that we use water as the reference substance. Water, of course, has a density of 1.00 grams per ml or 1.00 grams per centimeter cubed. All right. Again, an ml and a centimeter cubed are equal measures of volume. For gases, the reference standard is air. All right. Air has an average density of 1.29 grams per liter. All right. Again, the volume measurement that we use for gases that's most convenient is the liter. So thus the reference is also in that same volume unit liter, so grams per liter. Okay. So the equation for specific gravity, again, is a ratio, the density of the substance divided by the density of the reference. Well, these two densities have the same unit, so mathematically those units would cancel, and thus specific gravity has no unit. It is just a number. Okay, it's just a number. All right, so let me go on here and we'll do our two sample problems. Now, before we do these, I want to remind you of what we talked about yesterday in regards to our problem-solving method and my expectations of that. Okay? Again, I have them here on the board, and they're going to remain there for the rest of the year. So for any problem that requires a math calculation, make sure that you identify and label all the data and what question is being asked. Remember yesterday we talked about the APCE method. This is the A part, analyze the problem, all right? The planning part, all right? Write down the equation or the equations that will be used to solve the problem. C is compute, calculate. Calculate the answer, right? So you're going to write down the equation, you're going to plug in the numbers, and then you're going to calculate the answer, rounding it correctly, all right, based on the rules of rounding that we have discussed in previous lecture. And, of course, label it properly, all right? Another note on rounding, all right? Sometimes you have multiple operations to do. You know how to round based on that, okay? But, remember, it depends on what you do last. But, all right, you never round along the journey, all right? Never round along the journey. It requires multiple steps. You always save the long answer and keep that number until you get to your final answer. Then you round the final answer. We never do a step and then round, and then do a second step and round again, and then finally get to the final answer and round a third time. You do not do that. Now, on occasion, what I call an intermediate answer, all right, an answer before you get to the final answer. Sometimes that answer is asked for, all right, an intermediate answer is asked for. If that is the case, then you round it, all right, then you round it. But in computing the final answer, all right, you use the unrounded number before along the way in computing your final answer, and then again round that final answer appropriately. Okay? So unless an intermediate answer is asked for, you never round until you get to the final answer. If an intermediate answer is asked for, you round that answer. But you do not use that rounded number in computing the final answer. Okay? I hope you have that clear, because that's going to come up a lot. Okay? All right, so having said that, let's run through these two problems here and do what we're supposed to do, okay? All right, so we have a sample of soil that has a mass of 75.3 grams, so that would be our mass, M. Occupies a volume of 33.8 mLs, there would be our volume, V. What is the density? So we're looking for density and the specific gravity. So we're looking for two things here of this soil sample. All right, so we got looking for two things. So what reference standard? So what reference standard are we going to use for solids? Since soil is a solid, remember the reference standard for solids or liquids is water. And remember that its density is 1.00 grams per ml or 1.00 grams per centimeter cubed. Okay, so that will be our reference standard when we solve for specific gravity. So we need to solve for density first. So write the equation, E equals m over b. All right. Now we're going to plug in the numbers, 75.3 over 33.8. And it is asking for that answer, density. So we are going to round it. Let me grab my calculator here. So 75.3 divided by 33.8. 2.227810651. Well, it asked for this answer, so we need to round it. We are dividing, so we round by sig figs. According to those figures there, we're going to round to 3 sig figs. So that would round to 2.23 grams per ml. So here's the equation, here's the numbers, here's the correctly rounded and labeled answer. All right. Now, specific gravity is equal to the density of our substance, which in this case is soil, over the density of water, which is our standard. Okay, so the density here is 2.23. That was the rounded answer. Remember, again, the long answer was 2.2278100651 grams per ml. Density of water, of course, is 1.00 grams per ml. As we said before, those units cancel. Specific gravity has no unit. And again, we're dividing. The fewest number of sig figs is 3, and so the answer is 2.23. No unit. Now you're thinking, now wait a minute. All we did was divide by 1. So the answer should be the same as it was before. And for solids and liquids, that is true. All right, that is true. Numerically, they should be the same. However, keep in mind that you could have a difference in sig figs. You know, based on the data up here, maybe this answer would have been taken out more decimal places. All right, more significant figures. Let's say 2.227. All right. Well, then when you put that, then when you do your dividing down here, and now our number of sig figs is 3, we round to 3 sig figs, that 2.227 up here becomes 2.23 down here for specific gravity. So it is possible that the number of sig figs in these two answers could be different. It's going to depend on how precise your data is up there. So should they be exactly the same? In some cases, yes. In some cases, no, but they would round the same to the number of significant figures, fewest ultimately. So, but anyway, so keep that in mind. All right. So now, what does this mean? Well, this is what specific gravity is used for. It's used a lot in mineral science, all right, earth science. 2.23. What this means is this sample of soil is 2.23 times as dense as the reference, which in this case is water. So soil is 2.23 times as dense as water. So what does that mean? When you put the soil in water, what's it going to do? Sink, all right? So for solids and liquids, all right, if the specific gravity of a substance is greater than 1, it's going to sink in water. And if the specific gravity is less than 1, then of course it is going to float in water. That's what specific gravity is going to tell you. Okay? All right, so the next one. An empty container has a mass of 52.75 grams. There's a mass. After it's filled with helium, it's found to have a mass of 54.44 grams. So there's another mass. If the volume of the container is 9.66 liters, which of course then would be the volume of the helium, since the gas takes the volume of its container. B, again, what's the density and the specific gravity of helium? So we're looking for both of those again. What reference standard would we use for helium, which is a gas? Its reference standard for gases is air. And its density is 1.29 grams per liter. Okay? All right, so again, we're going to start by finding density. So M over B. So M, we need the mass of helium. All right, we're trying to find the density of helium, not the density of the container with the helium. So how do we get the mass of the helium? Well, here's what the container weighed empty. Here's what the container weighed with the helium in it. Just as I said a few minutes ago, we're going to find those two masses, or subtract those two masses to find the mass of the helium by itself. So we can do that right here. So 54.44 minus 52.75, or basically M2 minus M1, okay? Over the volume, 9.66. So this is a multi-step operation. We subtract first, divide last, which means we round by sig figs. And so if I do that, 54.44 minus 52.75 divided by 9.66, we get 0.17494824. Again, rounding to sig figs, and the fewest number of sig figs in our data there is 3, then we would round to 3 sig figs. So it would be 0.175 grams per liter now. Volume unit is liter. All right. All right. So these are both 3 sig figs. Sorry, I forgot to write that down. You don't have to write that down on your assignments or tests or whatever. I'm just doing it there for reference in case you forget why we rounded that way. So specific gravity this time will be the density of helium over the density of air. Air being our reference. All right. Now here again, this is a rounded answer. We would not use that rounded answer here. We would need the long answer. So that's why I kept it handy. All right. 0.174 94824 over grams per liter over our reference 1.29 grams per liter. Again, the units cancel out. Here we have a lot of sig figs, and here we have 3, so we'll round our final answer to 3, 0.136. And both of these are 3 sig figs. So, what does that mean? All right. Well, basically it means the same thing as specific gravity up here in the first example, except now our reference isn't water, it's air. All right. So for gases, if the specific gravity is greater than 1, it sinks in air now. Not water, it sinks in air. If the specific gravity is less than 1, it would float in air. Well, the value of specific gravity of helium is 0.136. That's less than 1. And as most of you already know, if you go buy a helium balloon or get one for your birthday or whatever, and you let go of it, up it goes. That's because it's less dense than air, all right? And so it floats in air, up it goes. If you blow up a balloon yourself, all right, you're exhaling CO2 in it. So if you've ever done that, which I'm sure you have, and you tie it off and you drop the balloon, it doesn't float up in the air, it sinks to the ground. Well, that's because the specific gravity of CO2 is greater than 1, because the density of CO2 is greater than air's density, which is 1.29. Okay? So sinking and floating not only, is in regards to water, but it also is in regards to air, if you're talking about gases. Okay? So, that's all for today's lesson. When you do your assignment, and in all honesty, this is probably one of the most important assignments you're going to do all year, simply because it's going to set a precedent. All right? These are my expectations for how you are to solve your math problems, your chemistry math problems. I've demonstrated that here. All right? So you identify all the data and the question being asked. You write the equation or equations. You plug in the numbers. You round correctly. You label correctly. All of those things count for points. All right. So, and as I said, I think earlier, most chemistry math problems of mine anyway are at minimum, 4 or 5 points, and there are some more extensive ones that are a whole lot more than that, 10 plus points. Final answer is only worth 1 point. All right. So if you skip any or a multitude of these steps, you're just scratching points off your score. All right. So why do that? Every point in here is precious, believe me. And so throwing them away for no reason is really not a very good idea. All right. So you get the right answer. You want to get 5 out of 5 for it, or do you want to get 4, 3, 2, 1, or 0 out of 5? Because I can tell you this: if you just write down the answer and show me nothing, nothing, just literally the answer, you don't even get a point. You get 0. All right. So, a very minimum amount of work will get you 1 if you get the right answer. So, all right, make sure you remember that. All right, some of you are going to learn that the hard way, but hopefully, once you've kind of been slapped in the face, not literally, of course, in regards to, I can't skip all these steps that he's talking about. You're right, you can't. I'm not going to let you get away with it, because in any future science, physics, chemistry, college level, whatever course, you're going to be required to show your work. It's not busy work. It's showing that you understand how to solve a problem, all right, and how you get to a final answer. And you may make a math mistake along the way and get the wrong answer. That's why you double check your math at the end, right? Evaluate, the last step in the APCE method, evaluate. Make sure it makes sense, all right? So anyway, you do everything right, get the wrong answer, you're going to get, if it's a 10-point problem, you're going to get 9 out of 10. All right? You do show everything you're supposed to, get the wrong answer, you're going to get 9 out of 10. So there again, a majority of the points are wrapped up in the method, all right, not the answer. Okay? All right, so until next time, be careful of what I just said. Do your best on your work. Make sure you show everything you need to show. I will be collecting it tomorrow. So until next time, Mr. Keister signing off. Stay safe, and I'll see you soon. So long, guys.